that standard electrode potential for a given cell is going to depend on what two half reactions are happening. It measures the potential energy difference between the two electrodes. So we can think of each electrode in each half cell as having its own potential, the standard electrode potential. And so this is like the elevation at the head and the foot of the stream. And the difference between them is the potential energy difference. So the standard cell potential here is the difference between the standard electrode potentials. So here we have this picture again. We have two water tanks or two beakers connected by a common pipe. This tank has higher volume of higher volume of water, and this is lower. We understand from just experience in life that the water in this tank is going to move to that tank until they're equal in level, right? Until the potential energy difference is gone. So when we have two half cells that are connected, the electrons flow from the electrode with the more negative charge, that's the greater potential energy, to the electrode with the more positive charge, or with the lower potential energy. So electrons are going to go from high potential energy to low potential energy, just like water does. Well, electrode potential in a half cell is not something that can be directly measured. And so this is another place where we decided what we were going to call zero. So we assign a potential of zero to a particular type of half cell, and then we measure everything else relative to that. And the 0 point that was chosen is called the standard hydrogen electrode, or SHE. Standard hydrogen electrode, we've got an inert platinum electrode in 1 molar HCl, and we have hydrogen gas at 1 atmosphere. And so we've defined that as 0. This is the reaction that occurs. The hydrogen gains electrons the hydrogen ions gain electrons to become a hydrogen gas. So that is a reduction reaction. And these electrodes are not especially easy to make. It's not just like, a solution of this and you stick a piece of metal in it, because you need hydrogen gas at a pressure of 1 atmosphere. But this is what they chose to do. So the standard cell potential is the difference in voltage between the cathode, the final state, and the anode, the initial state. Anode on the left, cathode on the right. So it's the final minus the initial. So it's going to be the potential of the cathode half reaction minus the anode cath reaction. Anode. What did I even say? It's the potential of the cathode half reaction minus the potential of the anode half reaction. That's what I meant to say. I don't know what I did say. So in that example, we can measure the cell potential, and it's plus 0.76. So the electrode potential for the zinc 2 plus half cell, the anode, can be found because we assigned the other electrode to have a potential of 0. So if the cell potential is the cathode minus the anode, then the cell potential here, 0.76, is the cathode minus the potential of the anode. So the anode is going to be negative 0.76. This more negative electrode potential means there's a greater potential energy for electrons at that electrode because negative charge repels electrons. So when we're looking at this, you can think of this as being negative 0.76, the anode has a negative charge. And the greater that charge is, the more repelled the electrons are, and the more they're going to flow in the other direction. So the electrons are going to go from a negative voltage to a 0 or more positive voltage. Because electrons want to get away from negative and go to positive. They're going from high potential energy to lower potential energy. The copper 2 plus ion electrode has a measured cell potential of negative 0.34 volts. So here, the half reaction has a more positive potential energy than the standard hydrogen electrode. And so it's got a lower potential energy for the electrons. And this anode, if we had that as the anode, is going to be more positive, and so electrons are not going to flow away from it. The more positive the electrode potential, the lower the potential energy of an electron at that electrode. So that copper 2 plus half cell is positive relative to our standard 0. It's going to draw electrons away from the standard electrode. The zinc half cell is negative relative to the 0, and so it tends to repel electrons. So by convention, just because that's how some people decided to do it, these standard electrode potentials are written for reduction half reactions. So copper ion gaining electrons, reduction is gain of electrons, copper ion is being reduced. This half cell potential is plus 0.34. For zinc being reduced, this cell potential is minus 0.76. Okay, so that's what the book talks about, and that's how a lot of people think about all of this. It never really worked for me. So here are my thoughts. If you want to do this, the potential of the cell is equal to the cathode minus the anode, then you're going to use the cell potentials for the reduction reactions that are listed in the table, this table. And there's the rest of the table. It's a big table. That's what the book is talking about. That's fine. So here it's final minus initial. The cathode's on the right. That's the final minus the initial. I find that to be very confusing. So this is how I think about it. You can also add the half reactions and add the cell potentials. So here, if I have 2H plus 2 electrons, this is the reduction reaction for the standard hydrogen electrode. And this is the reduction reaction for the zinc. We look up their standard reduction potentials, and what we can do here, instead of deciding, well, which one's the cathode and which one is the anode, look at the chemical reaction. So, oops. If this is the reaction that's occurring, where the zinc is being reduced, but the hydrogen is being oxidized, we can take this reduction half reaction and write it backwards. Yeah, I didn't leave myself enough space. So we would just change the sign on that. So 0 becomes negative 0. You do not multiply these by coefficients ever. So you reverse this equation, you change the sign on its E, and then you add them together, and then you add the cell potentials together. And I don't think I was supposed to do this right here because it doesn't really help that much. I think I probably have another example coming up. But what I like about this is it's a lot like doing delta H, right? If you reverse the reaction, you change the sign. And then you add the two things together, and you add these things together. And in my mind, that's a lot less thinking than, I don't know why I can never remember that equation. This is where we find all of our reduction potentials. And you have to be careful because some elements are in here more than once. Like here, permanganate ion can undergo two different reduction reactions, and the potential is going to depend on, well, which product are you getting? So the standard hydrogen potential is defined as 0. So if we have an electrode with a greater tendency towards reduction, that's going to be positive relative to that, and E0 is going to be greater than 0. If the electrode has a lesser tendency towards reduction, then it's going to be negative. And the cell potential, again, is the cathode minus the anode. That cell potential will be positive for spontaneous reactions and negative for non-spontaneous reactions. And that's really where the positive-negative thing gets very muddled in my mind. So let's do an example. Nope, I made myself go look it up. Okay. So we're going to use those tabulated standard electrode potentials to calculate the standard cell potential for this reaction occurring in an electrochemical cell at 25 degrees Celsius, and the equation is balanced. They're just telling us that so we don't have to worry about it. At 25 degrees is just saying, well, that's what all the standard potentials are measured at, and so we don't have to mess around with temperature either. So the way I would approach this is I'm going to look at the two half reactions. So I've got 3 Pb2+, and I'm making 3 Pb solid. And then I'm going to have 6 electrons over here. And I've got 2 chromium going to 2 chromium 3+. And that's giving off 6 electrons. Here, these equations have already been multiplied to make the numbers of electrons equal. So we're not going to worry too much about coefficients here. I'm going to go to that table and I'm going to look for one that has Pb2+ and Pb. So let's start here at the top. That's not right. No. Oh, here's Pb2+. and Pb, right? So this is lead 2 plus electrons. So this is a reduction reaction, and E0 for this is negative 0.13. So I go back and I look at this. This is also the reduction. So E0 for this is negative 0.13 volts. Because it's written exactly the same as what I found in the table. Do I multiply by 6? No, I don't. So now I'm going to look for this other one, chromium and chromium 3. I think this is in the bottom part as well. Oops. Let's see, here's chromium 3. Okay, so this is chromium 3 and chromium 2. That's not what we want. This one is chromium 3 and chromium. And so this is negative 0.73. But this is written opposite of what I have. Right? This has the electrons on the left side, negative 0.73. On mine, I've got the electrons on the right side. So I'm going to change the sign. Because what it showed us over there right, that's what it showed us. Here, I have chromium being oxidized, not reduced, and so it's going the opposite direction, so I change the sign. And now I'm just going to add these guys together, and I'm going to get 0.60 volts. Any questions? I'm just going to talk through the other way of looking at it. So I need to give myself a little space here. So what the book is talking about is that the cell potential is the standard potential of the cathode minus the standard potential of the anode. Which of these is the cathode and which is the anode? It's not obvious. Oxidation occurs at the anode. Which one's being oxidized? This is gaining electrons, that's losing electrons. So losing electrons is reduction. Gaining electrons is oxidation. So this must be happening at the cathode, and this must be happening at the anode. That's not right. Oxidation is loss of electrons. Oxidation occurs at the anode. Reduction is gain of electrons. Red cap. Reduction occurs at the cathode. Oh, I know the problem. So I changed the sign on this guy over here because I was doing it the other way. So when we go look this up in the table, that's what, 2 electrons. So this is what we see in the table, right? That's what we see in the table. And so we're going to take the cathode and subtract the anode. So we're going to take the cathode, the negative 0.13 volts, and we're going to subtract the anode, the negative 0.73 volts, and we're going to get 0.60 volts. Or, what I was doing here, I'm looking at the chemical reaction, I'm pulling the half reactions apart, just writing them as they are here. I'm going to go look up their cell potentials. If this reaction is backwards, I'm going to change the sign. If it's the same, I'm going to leave the sign. And then I'm going to add those together. That seems a lot easier to me. I don't really have to think about which is the cathode, which is the anode, which is oxidation, which is reduction. Which one of these matches the thing in the table? Keep the sign. The thing that has the opposite, the electrodes are on the wrong side, you change the sign on this and then you add them together. So that's the way I'll be talking about this. Any questions? It's not confusing at all, is it? You have to work with it a little bit, get your mind around it. Okay, an electrode has a negative electrode potential. Which statement is correct regarding the potential energy of an electron at this electrode? An electron at this electrode is a lower potential energy than at zero, a higher potential energy than the standard, or the same. What I did there. So it has a higher potential energy. Its potential is negative. You know, I really don't like this question. It's really hard to think about. Because it seems counterintuitive. Let's not think about it. It's Monday. Okay, predicting the direction of spontaneous reaction. We're looking at E0 for each half reaction. The more negative one tends to lose electrons. Okay, so how do we think about this? Well, if it's more negative, the electrons want to go away. The one that's more positive tends to gain electrons, attracts electrons to the positive side. That's the reduction. So this is one thing that we do have to remember. For spontaneous reaction, the cell potential is positive. So if we look at those half reactions, any reduction half reaction is spontaneous when paired with the reverse of a half reaction listed below it in the table. Well, switch them so that you have an oxidation reaction and a reduction reaction. Adjust the signs, add them together, and see if it's positive or not. Negative charge repels electrons. Electrons move from the more negative to the more positive. Oxidation is loss of electrons. Oxidation occurs at the anode. I mean, these are the sorts of things you have to just sort of think through, because I'm pretty sure if I don't remember those easily, you're not going to remember them either. Okay, predicting spontaneous direction. So here we don't have to go back and look at the table, we pulled those out for us. So nickel ions being reduced and manganese ions being reduced. The spontaneous situation is where we add these up and we get a positive number. So let's just be Monday lazy and try both situations. If we do nickel going to nickel ion plus 2 electrons, I've reversed the direction of the half reaction. I'm going to change the sign. I'm writing this one in the same direction, and so the sign stays the same. When I add those together, I get a negative number. Oh, let's actually do the math. .95. Is that going to happen spontaneously? No, it's not. So what's going to happen spontaneously is the other direction, right? And we could write all that out. Let's just change the color here. So the other direction is nickel 2 plus 2 electrons, making nickel, and manganese making Mn2 plus and 2 electrons. So E0 for this one, this is exactly the same as this one up here that we looked up in the table, negative 0.23. Oh, my 0 fell down. And here, this is written backwards of that one, and so I changed the sign. I add them together, I get a positive number. So this is what's going to happen. I didn't mean to do that, but I guess that's okay. This is what's going to happen in a spontaneous reaction. So if we need to draw the cell or write the line notation for the spontaneous reaction, we're going to look at these, and we want the anode on the left, the cathode on the right. Oxidation at the anode. Oxidation is loss of electrons. Okay, this is the one that has loss of electrons. That one's at the anode. This is the reduction at the cathode. That one goes over there. Without calculating the standard cell potential, predict whether the redox reaction is spontaneous. Sketch the electrochemical cell in which the spontaneous reaction would occur. Label the anode on the left, the cathode, and the direction of electron flow. So we need to find these in the table here. So there's zinc and zinc 2+. And here's nickel and nickel 2+. Now, what's a little disturbing here is that there's no cell potentials here. So let's just go back and look at the table. Where is it? There it is. So the reduction half reactions, these have a high tendency toward reduction, and it goes to a lower tendency towards reduction. These go from positive down to negative. So if I want a combination of two things to have a positive sum, I'm going to reverse the lower one to make it positive and add it to the higher one. So these are reduction half reactions. The top is the highest, wants to be reduced, and the lower one wants to be reduced less, right? So I'm going to flip the bottom one. So this one would be flipped right here, zinc on the left and Zn2+ on the right. And that's what I've got going on here. So this one is higher than that one, and so this is the guy over here. So this also works into the analogy I had for the reactivity series of metals. So nickel is higher on the list, and so nickel is more likely to take the electrons. Zinc is lower on the list, zinc is less likely to take the electrons. So we've identified that this is spontaneous. And so the nickel, is it being oxidized or reduced? Oxidation is loss of electrons, reduction is gain of electrons. Is the nickel losing or gaining electrons to become an ion? It's gaining electrons, right, to get rid of those charges. So reduction is gain of electrons, and this one, oxidation, is loss of electrons. So this is being reduced, that's being oxidized. You probably will be asked to draw a cell. It does not have to be pretty. So the anode is on the left, the cathode is on the right. What happens at the anode, oxidation or reduction? A is a vowel and O is a vowel. Oxidation happens over there. So this is our zinc metal, and this has zinc ions in the solution. Reduction occurs at the cathode, and so this is where we've got the nickel ions and the nickel electrode. And it wants to know the direction of electron flow. Well, for a spontaneous cell, with the anode on the left, the cathode on the right, the electrons are always going to go from left to right. That means that this is losing electrons, right? Which is the oxidation. This is losing the electrons. The electrons are leaving this side and going to that side. And then a lot of times it will also ask you to show the direction of movement of the ions in the salt bridge. So we've got positive ions and negative ions. Which direction are the negative ions going to go? Are they going to go over here, where all the electrons are going? No, they're going to go the other way, because the electrons left, and so this needs more negative charges. So the negative ions are going to go that way, and the positive ions are going to go this way. Questions? How much is left? Oh, that's, no, we're just going to stop there.